When this heavy copper switch closes, we expect the electricity to reach full strength the moment the contacts meet. But if that circuit contains a tightly wound coil of wire, the current behaves strangely. Instead of spiking instantly, it ramps up slowly, struggling to reach its maximum value. The coil generates an opposing force to fight the new current, creating an internal pushback that prevents the flow from peaking immediately. This is back EMF. It is an induced voltage created by the coil's own changing magnetic field, and it pushes directly against the source voltage. A coil actively resists any sudden changes to the electrical current flowing through it. In this diagram of an isolated coil, the magnetic flux rises in direct proportion to the current. We define this relationship using the constant L, called self-inductance, a mathematical measure of the coil's physical properties. When that current varies over time, Faraday's law dictates how the fluctuation induces the back EMF. The negative sign represents Lenz's law, proving that the induced voltage always opposes the change in the current. The variable L measures how fiercely a circuit fights variation in its electrical flow. To physically maximize this pushback, engineers look to the geometry of the component. This 3D wireframe reveals the primary geometric variables: the density of the wire turns, the cross-sectional area, and the total length. Combining these variables gives us the formula for the self-inductance of a long, air-filled coil. We can increase this resistance without expanding the coil's size by altering the core material. Inserting soft iron introduces relative permeability, a measure of how it amplifies a magnetic field, acting as a multiplier in our final equation. By altering the shape of the coil and the material inside it, we dictate exactly how much a circuit resists change. Observe the difference between a hollow coil and a heavy iron core coil. When hit with the same voltage pulse, current in the hollow coil shoots up immediately. The iron core coil forces current to struggle, rising slowly towards its peak. The delay in the high inductance coil reveals that it takes physical work to overcome the back EMF and establish the flow. Once the current is established, it is stored as magnetic potential energy, described by this equation. This mirrors the formula for mechanical kinetic energy. Current functions as velocity, and inductance functions as mass. This is electrical inertia. Inductance plays the same role in a circuit that mass plays in physical motion. Self-inductance is the electrical twin of physical mass, providing the necessary inertia that prevents instant, chaotic changes in the universe's circuits.